Good morning, everyone. My talk today is going to be entitled Principles of Biosecurity Surveillance, and basically what we're going to do today is talk about, I'll give you a background and introduction to what I define as what's biosecurity. I'll start off by giving you some evidence of what we call globalisation and what the potential impacts are of this phenomenon. We'll then go into a review or overview surveillance problems and the solutions that we can encounter, in my opinion, and back this up with some operational examples that I built in New Zealand a few years ago. And at the end, we'll tidy this up with a possible discussion of possible strategy for the Northern Territory in terms of what we can do in terms of surveillance for plant pests. Now, this talk was originally titled Principles of Surveillance to do with plant pests, but I believe that if we have robust principles, then we can apply them across different sectors. So this is based on a previous presentation that was done a few years ago at the Global Biosecurity Conference, and I've been doing this talk for quite a few years now and developing it as I go, so hopefully you've got the final product here. So what is biosecurity? There's a lot of definitions out there and it depends where you're coming from, but I define it as a set of systems, activities and behaviours that serve to protect an environment and people from invasive organisms. And this is undertaken by a lot of different groups, whether it's industry, state, commonwealth, and even the public. So it's something that a lot of people participate in, and it's quite important activity. And biosecurity is actually, although we've been doing a lot of activities, the term biosecurity is actually a relatively new phenomenon. You'd actually struggle to find it in a dictionary, for example. Now, biosecurity is ruled by what's called the Biosecurity Continuum, which describes three distinct properties. So we talk about pre-border, border and post-border activities that we undertake. So pre-border is looking at the risks offshore, for example, and trying to mitigate some of the issues before pests come into the country. At the border, we obviously do inspections for pests and diseases that might come in as contamination or as actually on its products themselves. And at the border, we might want to do surveillance and perform other activities to detect these organisms. And in post-border, we're looking at, again, detection and doing a lot of activities there. In reality, I think the biosecurity continuum is misleading, and I think it's wrong in some ways. This is similar to the biosecurity continuum, but this is what we used in New Zealand and the Forest Biosecurity group I worked in. And we talk about some of the similar stages. We talk about pre-border, border, and post-border. But what we're actually trying to do is mitigate the risk at each of these stages. So we have intervention points at pre-border, border, and by doing surveillance. And hopefully we try and mitigate the risk before pests actually get into the area that we're trying to protect, for example, forests or mango plantations or something like that. So I think it's a different way of looking at it. And I think, again, that's still not capturing what we should be looking at in terms of biosecurity. I think biosecurity is actually, the system is actually a network. It's not a continuum. And this is just a mock-up that I made a few years ago, trying to look at the linkages between different parts of the system. So again, we still see pre-border and border, but we should be looking at specific nodes. So we're looking at, obviously, surveillance, risk analysis, response, and diagnostics. And we should be treating the biosecurity system more like this. And what we need to look for is linkages between these systems, feedback loops. And one of the key points I'll be emphasizing today is the similarity between surveillance and response. So we're looking at a biosecurity system. Its job is to collect information to make informed decisions. And this is a better way of treating that system than looking at the so-called biosecurity continuum. So there's many drivers of surveillance. We need to ask, well, why do we do surveillance at all? And one of the key drivers is obviously to provide access to markets for products that we want to sell. So market access is a huge driver. And we can look at that both in terms of international and interstate in the case of Australia. So we also have international obligations, for example, under the World Trade Organization. There's a lot of standards and specifications that describe activities we should be doing. For example, ISPM, International Standards for Phytosanitary Measurement. Well-collected information will also assist us in managing existing pest populations. We can understand changes in pest behaviour, for example, associated with climate change. Do we get changes in population distributions or sizes or dynamics? And we'll look at a moment at the potential cost benefits of actually making an early detection. We can also, one of the fundamental roles of surveillance is actually to measure the leakiness of the biosecurity system, because it doesn't matter how much money we spend at trying to prevent things coming in, some pathways are unblockable, and also under international obligations, we can't completely close some of these pathways. And there's also an expectation that globalisation may increase the rate of invasions, which means that surveillance should be becoming increasingly important and better funded. So, are there benefits from surveillance? Well, evidence is starting to accumulate now, and what we see here is a graph from New Zealand. And what this is looking at is we had a large number of pest moth introductions and subsequent eradications. And what this graph is showing is that the smaller an area of infestation that you can find a pest, which is generally associated with the faster you can find it, there's a distinct advantage in terms of cost of eradication. So the species we're looking at here are FWW is full webworm, GM is gypsy moth, WSTM is white-spotted tussock moth, PAM is painted apple moth, and GLS is a gumleaf skeletonizer. And there's actually two invasions of gumleaf skeletonizer. One was found on a couple of trees at the time of detection and eradicated. The second one, it was so well distributed that an eradication was considered unfeasible. So what this shows is that the sooner you find something, by having a robust or a good quality surveillance system, you can actually get a cost benefit out of that. So globalisation, there's certainly a lot of evidence that in the last 20 years or 25 or 30 years that the rates of goods moving around the world have increased. So this is looking at TEUs, which stands for 20-foot equivalent unit, which describes a standard shipping container. And shipping containers have increased in popularity because it's a faster way of moving goods around. Previously, ships used to be loaded in bulk. So sea containerization had a huge impact on trade. And as you can see, even in Australia, even because of the scale, you can't see that it's increased significantly, but it certainly has since the 1980s. And you can also understand that from this graph that even though we have a lot of risk coming to Australia, it's dwarfed by sort of global patterns in terms of Europe and USA. But the trend is there for all these areas. So there's more risk coming in than ever before. Air passengers, which is another risk pathway, this is specifically for Australia, and you can see that this pattern has increased over time as well. So we get a lot more risk goods coming into the country over time. And the volumes are becoming so large that it's really, really difficult to implement some of those pre-border and border inspections. So it's left up to surveillance to try and find what gets through. So this is data I had from DAF and I mapped out, and this is the actual reported rate of invasions for Australia. And the significant thing we see here is that the trend actually seems to be decreasing over time. Our expectation based on globalisation is that this should be increasing. Now it's important to note here is that there's a difference between the rate of discovery, our detection rate, and the rate of invasions, because we're not actually measuring the rate of invasions, we're just measuring the things that we actually find. And I think one of the problems that we have in terms of the line going down, and we expect it to go up, is that a lot of things may be coming in repeatedly. And we might be getting new genetic populations coming in, but because we've discovered something once, we assume that's the only population that's come in. So there's a number of reasons why we may actually be underestimating the rate of pests that are coming into the country. Now, I talked about our inability to completely close down a lot of pathways, and wind would be a good example in that we've got virtually no ability to stop wind transporting insects, for example, from nearby areas, Asia region. But we've also got to understand that trade pathways that are regulated under the WTO cannot be sealed completely. And this is because we can set what's called the acceptable level of protection to a very, very low but non-zero level. So we can't enforce regulations that reduce that to zero. So we have to accept that there is going to be a built-in leakiness into the system. And given enough sampling events, invasions will happen over time. So overall, we have to accept that incursions are not a failure of the system. They are going to happen, and we need to do surveillance to find them in time to have some benefit. So when we describe surveillance and what we do, we need to describe more accurately in terms of what sort of detections we're actually making. And these were described, I described these detections to try and clarify what we're achieving with one of our programs called high-risk site surveillance. which we'll talk about soon. So the key driver is obviously to make the first detection of an invasive organism, and we call this a primary detection. So we're talking about a new invasive exotic species, and in some cases we're actually talking about discovering a new to science species, which may or may not be indigenous. In some cases we don't know if it has actually been introduced or has been here for a long time. The second class is what we call secondary detections, and this is to deal with species that have already been recorded in a country such as Australia, but we're looking at a change in an extension of distribution, for example. And that, again, under climate change, it's one of the tasks we're charged with, is to monitor if insects or pathogens are increasing the distribution. And we also need to understand the host ranges of species, and we need to monitor if there's changes in behaviour, and that could be an indication that we're getting new genetic material coming in. There's a number of species for which different biotypes will have different host ranges. So that's crucial information as well. And in New Zealand, the methodology we use to describe a distribution was called the Crosby system, which divides, it's based on Crosby et al., and it divides New Zealand and some island areas into 37 distinct bioregions. So if we have a pest, for example, in Auckland, and we find it in the area WO, which stands for Waikato, we would generate a new secondary detection. So it tells us that organism is now into a new region. And some species will, if you've got sufficiently robust surveillance systems, you should be able to track these species moving around, which helps identify if you need to implement risk mitigation measures in different areas. And then there's a final class, which is new, and this is called a significant detection. And this came up where we had a detection, we were running an eradication for a pest species, and with an eradication you usually define a period of time which you survey for without a detection, and you can declare it eradicated. And what happened is, in this case, is that the program was running for 2 years, and in the week before the species was to be declared eradicated, it was actually found again. Now, that species already had a primary and secondary detections, but they weren't covering what the impact of this. And so what we're talking about is there's two different types. There's a new life stage discovered. So, for example, for fungus, we could talk about an anamorph versus teleomorph, which is sexually versus asexually reproducing life stages, which again suggests that we've had new genetic material come into the country that wasn't there previously. Or in the case I was talking about, a species is under eradication and it's been detected either in the eradication zone, which has big implications, or it's been detected outside the target eradication zone, which might mean that you have to start the whole program again. So, but the optimal goal, what we're always trying to achieve with our surveillance, is to provide what we call an effective detection. Now, this is a moving target, and it may not always be possible, but we define it as detection of a population at a point in time where all management options are available, including eradication. And if we detect something too late, eradication may not be feasible. We also want the costs and social environmental impacts to be minimised if we have to manage it, and we have to realise that for some species this is not possible. And there's certain insect groups, for example, which have never been eradicated because of their biology. They just spread too fast. So let's get on to the stage of talking about surveillance problems and what I think are some of the solutions to them. So the first one is, and this should always crop up when we're talking about surveillance, because we always have limited resources. So we need to understand, well, if I have limited resources, where am I going to apply them to get the maximum benefit from them? So what I think we should be doing is applying resources where the probability of incursion and hence detection is greatest. And we know that pests arrive through pathways, and that these should be where we focus our limited resources. As I said previously, some pathways aren't controllable, but we need to be able to map pathways and look for the risk patterns. And something's fallen off the bottom there, but what it's saying is we also need to survey, as part of the strategies, we also need to survey as many plant species as possible to detect the broadest range of pests as well. A lot of organisms will come in through a pathway, for example, a sea container, end up in an industrial area, and its host might not actually be there, so they'll actually disperse to find their hosts. So the next issue is that biological invasions are spatial in nature, but spatial data is very, very poorly used to allocate surveillance resources. And I think this is fundamental, is that we need to understand where they could come from and deploy our resources in those areas. So without spatial data, we're basically flying nearly blind, and we can't make informed decisions about where we're allocating our resources. And just as importantly, we can't justify to, for example, other states or jurisdictions that we're putting our resources where they are best applied. So we need to understand what the risk patterns look like, and it's unique for every city, every state or territory, any sort of geographical region that we want to describe. Spatial patterns will be different, so we need to understand it. So we need dedicated GIS and spatial databases to capture this information. And risk changes over time, so mapping the system out now, today, and using exactly the same data in 10 years just won't cut it. We need to understand on a year-by-year basis how risk moves around. And we need to understand that where something was 10 years ago, even if those risk sites are gone, there's still a residual risk. There's still potential for populations to be there that we haven't detected. The next issue, and this is a bit of a thorny one, is, well, what pests do we look for? And this is critical. And I call this the folly of pest lists. And this is more of a reaction to a system I was asked to design, where I was asked to look at thousands and thousands of species and pick a set of winners. And the idea was that we were going to deploy pest-specific surveillance tools such as pheromones and lures and stuff to find them. And to me, it was immediately obvious that if we're going to do that with pest-specific tools, we actually ignore a huge range of species that are actually probably turning up that aren't associated with those. They can't be detected by those tools. And this was obvious in New Zealand. A lot of those moths that I talked about, gypsy moth we were targeting, but none of the other pests were on our lists, or we didn't have tools for them. So I call it the folly, because these pest lists I think it's a dangerous direction to put all your resources into. Now, in terms of developing pest lists, the tools have developed considerably through organisations, for example, as the SARA, the Australian Centre for Excellence in Risk Analysis, and the cooperative research centres. But still, it should be a tool that we use in conjunction with other surveillance methods. And we can, obviously, we want to be able to predict some pests that we are really concerned about. For example, in the Northern Territories, we're obviously concerned with fruit flies. So yes, we should be, that's one of the pest-specific programs we should be running, but we need to understand that pest lists have absolutely no predictive value at all. And we need to take that into consideration when developing a surveillance strategy. So we need to distinguish between having a strategy, surveillance strategy, and surveillance tactics. Looking for fruit fly is one of the tactics, but it's not a complete strategy by itself. So this is encapsulated in the fact that no one survey method is perfect. So pheromones can detect either one species or a small group of closely related species, but reliance on these tools leads to huge gaps in your detection capability. The other option is to have broad spectrum visual surveys, people walking around surveying vegetation, but again, we're not going to be able to find everything, and some tools, such as pheromones, will actually find a population a lot quicker than visual surveys. So the solution that we used in New Zealand was to deploy a dual arms approach. So the emphasis was having on a broad spectrum surveillance program to deal with uncertainty, to detect all the invasives that we couldn't predict that aren't on pest lists. And then you augment that with your pest-specific tools and target key crops where there's a clear and present danger, for example, gypsy moth and fruit fly. I mentioned this briefly before, a lot of the pathways are actually what we call vegetation poor areas. So, for example, if we have a container facility or a container park where we know there's a very, very high risk, that site may actually contain no vegetation or very, very limited distribution of plant species. And you'll see this around Berrimah, where we're located. Apart from Berrimah Farm, it's almost a desert out there. You tend to get the same species over and over again. So how do we deal with this? Well, basically the simple solution is to survey nearby areas of vegetation richness. And again, we need the spatial data to understand what we're dealing with. So we define the risk site areas into two types. So we define risk site areas which represent actual pathways themselves. So we're not just talking about sea containers, we're talking about, for example, with tourist hotels, motels, caravan parks, camping grounds, things like that. But again, caravan parks have tend to have a lot more plant species than industrial areas, but you tend to get the same species over and over again. So we're not fully representing all the plant species that are available for surveillance. So next to those risk site areas, which we may or may not survey, we identify the vegetation-rich areas, which have a lot more botanical richness, and this helps expand the range of species that we survey. And it's worth noting that some vegetation-rich areas are themselves, in fact, risk site areas, such as the botanical gardens in Darwin. But very few risk site areas are actually vegetation-rich areas. Now, another critical problem is that detections, I don't think, should be actually used as the sole criteria for describing the performance of our surveillance systems. And the reason is that they're just not a reliable indicator. This is because, and they're still important, but this is because a detection itself does not mean that you have a very good surveillance system. Now, I tend to think of surveillance we have three phases of surveillance. The first phase is that we don't do anything. And for the vast majority of pests that we're worried about, or a huge number of crops, we don't actually do any surveillance. And that's understandable. It costs money. We can't allocate it to everywhere. The second phase is that we do something, whether we survey some caravan parks or things like that. And the second phase, so basically we're out there doing some surveillance activities, but it's not what we call technically robust. But the advantage of that system is that it gives you the possibility of actually detecting incursion. And some fairly average programs in New Zealand did make some good what we call effective detections, just by the fact that they were out there looking for something. But similarly, a lack of detections for a program doesn't indicate that you have a poor quality program. The gypsy moth program we ran in New Zealand ran for 10 years without making a detection. So there's a lot of a lack of political will to keep funding that program, because people don't like to fund things that don't find their target pest. Subsequently, they did make a detection again at the very end of 10 years, and it led to eradication. But this lack of detections, we need other ways to describe the quality of a program when we're not actually finding things. And for pest-specific surveys such as fruit fly, our target organism may never turn up. So we need to be able to defend our position and say, look, it hasn't turned up, but we do have a high-quality system. But we need to be able to prove that. So the solution is information, and information is not just the currency for surveillance, but it's the currency for the whole biosecurity system. So we can use a number of tools here. So we can talk about collecting perfect data sets. Now, for example, for gypsy moth, we want to describe all the sea container sites where sea containers move around in New Zealand, and would also, in that particular case, want to describe where all imported cars end up in New Zealand, because we don't have our own we didn't have our own local motor industry. All vehicles were imported, and the vast majority were second-hand cars coming from Japan and Asia, which is very, very high risk areas for gypsy moth. So in that case, we had two discrete layers we wanted to map out for gypsy moth: sea containers and vehicle sites. So what we want to be able to do is describe at a given point in time the completeness of our knowledge about each information layer. And we use that as the benchmark at a given point in time in terms of we're allocating our surveillance resources based on a given level of information, but where does that information range between 0 and 100% of possible knowledge? And again, as I said previously, we need to date stamp that data and compare completeness over time. And if we can show that our knowledge of a risk layer has increased over time, that's one of the descriptions of an increase in quality of our program over time. So the solution is to use information itself as the metric. So improvement in knowledge indicates that we're making more informed decisions. It doesn't guarantee that you actually make a detection or that an organism doesn't turn up somewhere else, but it's also okay not to have all data. There's a number of spatial layers where we won't be able to collect any information, but 0 is not a failure. It just indicates that if we had more resources, we could collect more data. Another issue is the variable funding issue. And so the paradigm I use here is that I call it funding determines detection probabilities, not the other way around. Now, I've seen people who have described how much it would cost to operate a surveillance program that would give them 99% detection probability for a pest, and basically it was going to be too expensive to do, so they didn't do it. Now, that's not a good way to go around describing surveillance. We actually need surveillance that can operate at a number of different a whole range of different detection probabilities. And what we do is, if we've got funding, the funding will actually determine the strength in terms of which we can deploy our surveillance effort. Now, the issue with funding is that funding can vary over time, not just only vary, but it can stop and start over time. So we need surveillance systems that can actually respond to the situation. And so these funding issues actually end up, because they're stopping and starting and they're not guaranteed, you end up with what I call ad hoc surveillance programs, where you haven't got the long-term funding to develop a robust system. So you end up doing the same old, where you don't really develop the system. You're in phase 2 continuously. You're doing something, but you're not actually achieved exactly what you need to do. So the reality is funding changes over time. Funding may stop-start, and this leads to ad hoc approaches, whereas the number of risk sites that we may be dealing with can actually increase over time, and we've seen that with globalisation. The number of tourists, people coming in, the number of risk goods coming in, that actually increases, whereas our funding may stay the same. So how do we cope with this? Well, the solution is scalability. So the ability to scale up and scale down our surveillance techniques. So we want to be able to have a surveillance program where we can respond to these changes in funding. And this may involve either a reduction in surveillance effort, or we may end up, for example, with fruit fly in terms of spreading our traps a lot further out, which obviously reduces our detection probabilities. So funding, in effect, does determine what levels of detection you can provide. And geometric scalability is often the solution, and we'll see this in a moment. Another key paradigm in biosecurity is that surveillance equals response. And this took a long time for me to get through to people, but once they grasped it, it has all sorts of implications for a biosecurity system. So the difference between surveillance and response is just basically one of scale. So with, for example, a surveillance program, we're not sure something's actually there. So we may have to survey over large areas at a very low detection probability. We will be surveying for long periods of time, years and years and years, and we have limited resources. So that's why we're going to operate at very, very low detection probabilities. When we actually find something, and we are going to move into a eradication phase, spatially, you're going to be targeting a limited area. It might be a city where that, for example, that pest is turned up. In terms of timing, temporal issue, you'll be surveying for a specific point, specific duration. You'd want a number of life cycles without making a detection to declare it eradicated, or you go for a predefined time limit, for example, 2 years without making a detection. And in terms of resources, you're going to have a huge amount more resources available to you than you have available for the national surveillance program. So our general surveillance, as I said, it's an issue of scale. So we need, and one of the other advantages of understanding scalability is that we can if we design a surveillance program for something, and we don't actually have to operate that surveillance program, there's no rules saying you can't design surveillance ahead of time without having funding. But if we have that surveillance program ready to go, we know that if we're having a response, we can operate the same surveillance program at a different scale. So by building one design, we are able to cover this whole gambit of from surveillance to response activities. The other issues we come up with, and this is because we've got limited resources, so how do we compare different types of risk site? So this is the apples and oranges issue. So how do I compare, if I can only survey one site this year, I haven't got very much money, how do I compare one trade site with one tourist site? If I've got 1,000 sea containers coming in for a site, is that more important to survey than a tourist attraction with 1,000 people going through that? I don't know. What if I had 10,000 people going through that tourist attraction? Would that be the same risk as 1,000 sea containers? So we need to be able to compare these quite different risk pathways. So we can estimate risk not only in terms of volumes of goods, but we should also be looking at the risk associated with those goods. For example, not all sea containers are created the same. They're not all equal risk. So again, another layer of information that we could use to inform these decisions is where are these sea containers coming from? Some nations may be higher risk, some areas may have high contamination rates. So we can't just treat everything as exactly the same, having the same level of quantifiable risk. So we'll move on to examples now of actual surveillance programs that are in operation in New Zealand and try and address some of these principles that I've been talking about, and hopefully prove that they can work in the real world. So the first example is a program called High Risk Site Surveillance, which became operational in 2005 in New Zealand. And this, I understand at the moment that this surveys what we call 10,000 what we call transects, and we'll look at those in a moment. So this, this operates at a national scale. It focuses on trade and tourism pathways, and it has a forestry background. So we focus on what we call arborescent vegetation or forests, and it sounds like we're not actually doing a hell of a lot, but when we describe forestry, it's quite broad. So we're talking the native forest systems, we're talking about all the native plants that we'd be interested in. We're talking about commercial plantation forests, so we're interested in eucalyptuses and Pinus radiatus and things like that. And we also talk about the urban forest. So the urban forest is all the plant species that are around us in the urban environment. So even though it sounds like it's not a lot, that's basically encapsulating a hell of a lot of plant material. We don't tend to focus on ornamentals and little flowers and things like that. And we certainly don't focus on weeds. But it's quite specific about what this program is specifically named High Risk Site Surveillance, because that's its job, to focus on these pathways. And we don't do anything else. So it's based on transects, where we do intense visual surveys of small transects. And so it used to be extensive. It used to be people walking around a park. They see some damage in a tree, a dead, dying tree, and they would respond to that. Now, the issues of running a surveillance program like that, which is, I have to say, is fairly similar to what we do here, is that the only data that we capture is in terms of if we take a sample, we record the plant species that we've surveyed. We don't record all the plants that we looked at that don't actually have anything. And that's a huge gap. We're doing a lot of work, looking at a lot of plant species, but we're only reporting that we've looked at a few plant species. So that's one of the big issues in terms of validating that we have area freedom for a particular pest, is the ability to prove that we've surveyed a large number of plant species. And this is why we use transects. So in terms of spatial data, we're focused on pathways, and this is an example. This is some industrial suburbs in Auckland, and the program was basically developed because we had a significant issue in terms of biosecurity principles going on. In terms of New Zealand used to have 12 international ports. So these programs used to be called the Port Environs Surveys. Because of increased containerization and globalisation, it was becoming unfeasible to survey all these containers at the ports and then release them into the environment. So in their wisdom, the biosecurity authorities decided to deregulate container devanning, or some people call it unstuffing, and let the importers actually devan the containers and inspect them themselves. The implication is we went from 12 pathways that we could survey over 7,000, with a huge spatial distribution over New Zealand. You see the précis mapped over in the top right-hand corner. So the yellow dots there actually represent the ports that we used to survey, and the red dots indicate the areas that we now have to survey. So our job changed fundamentally in terms of spatial scale. So mapping, by mapping these aggregations of these transitional facilities, we could see that a number of these areas were clustered. And there's lots and lots of outliers, but the vast majority of sites were occurring in industrial areas, which is actually beneficial for surveillance in terms of we can deploy a small amount of resources in a given area and actually cover a large number of risk sites. But you can see here what I mean by understanding the spatial nature of the risk that you're dealing with. If we didn't have this data, we'd be flying blind. That's just one pathway that we're dealing with. This data here is actually some commercial data that I bought. So these are other spatial layers that we need to actually do our job. So obviously I talked about the motor vehicles that we need to map. So motor vehicle dealers would be a risk pathway in New Zealand, not so much here. But the accommodation layers, you've got over 3,000 accommodation layers that we've now got mapped. Motor camps, caravan parks, hotels, motels, rubbish collection and disposal. And that's an interesting one because that's not a site we would survey. But you need to take the philosophy of any site that we would survey in a response should be mapped in our surveillance systems. And they're used in responses, for example, with some of those moths because there were vegetation controls, and infested vegetation can be moved into these rubbish dumps. So there are areas that they would survey in a response, but we're not going to survey in terms of our general work. research institutions and scientific institutes, very, very high risk areas. People behave badly. People bring things in either knowingly or unknowingly. So we've got to take those into account as well. Zoological gardens, botanical gardens, all sorts of things like that. And we also were able to map out a huge number of sporting and recreational clubs, and these are part of our vegetation-rich areas. So we identify where all these parks and reserves are spatially associated with our risk site pathways. So you can see this cost me about a bit over $4,000, but I gained a data set of 11,500 data points, which again really, really helps us understand where risk is lying in New Zealand. So here's an actual example from the high-risk site surveillance program, and here we're showing the risk site areas and the vegetation-rich areas that are associated with them. And we're also showing here how we can crudely rank some of the risk sites. So the areas that are green are our vegetation-rich areas, so they're parks and areas of botanical richness. The areas that are coloured, ranging from yellow, orange, red, and purple, are actually the risk sites, the industrial areas. And what we've done here to rank them is basically count the numbers of containers that go into each one of those areas. So we now need to be able to describe as a polygon those risk areas and then count the number of risk goods that go through them. So you can see that if we I could only survey one of those sites, it'd be one of those areas that are in purple, which are receiving over 10,000, between 10,000 to 100,000 containers a year. So this is a very, very crude way of ranking these risk sites. And you'll notice those the circles are within some of those sites. Those are called VINs, or Vehicle Inspection New Zealand, and we identify them as risk sites because that's where imported Japanese vehicles go to be inspected before they can get registered in New Zealand. So again, we can associate a value with those particular sites. We could assign a weighting, so sites that hold those VINs and those inspection sites could actually go up our pecking order in terms of surveillance resources. And again, you see on the Précis map the sheer scale of areas that we have to survey or allocate our resources. So the transects is a critical change from just having a walkabout, because it gives us a repeatable, replicable sampling mechanism, and it also gives us data capture. So each one of these transects, we capture all the plant species that are in there, and that goes into a database. Now that's not just useful for reporting to whoever's interested in terms of what plant species we survey, but if we come to a response, we find a new organism, we know its host, we can pull up any of those, interrogate any of those 10,000 transects we have and ask which of these transects contain these particular plant species. So in a response that is a time-critical situation, we can immediately identify within a given radius what areas we should be going to survey these particular plants if we want to delimit a population really, really quickly. The advantages of transects is that's the standard ecological sampling tool, so it's not going to be controversial. Allows replicable surveys, and importantly, we're actually doing surveillance now where we can calculate detection probabilities. It's pretty hard to calculate a detection probability of someone walking around a park, particularly someone who surveys it the next year, they don't know where the other person walked around. So, and of course, transects are scalable. So we can scale either the size of the transects that we're using or the numbers that we do in any given area. So if we lost half our funding, we'd just reduce the number of transects that we actually survey in a given year. Now, how do we calculate detection probabilities in this case? It's just geometry, and it's been known for a long time that if you have a circular infestation in a given area and you randomly apply a line, such as a transect, you can calculate the probability of actually intercepting that incursion. So the more transects you have, the higher your probability goes. So it's been used in New Zealand for a long time in terms of forestry surveys. So the more survey plots you have, the better, and you can look at the parameters of the transects in terms of their width and length. And when we map this out to, if you're just looking at the top line there, that's talking about if you just use transects, the more transects you put in, you've got the higher probability of actually detecting circular infestation. Now, the reality is that a surveyor could be in a transect that intercepts an infestation but doesn't actually detect it. All insects and pathogens, they're not 100% detectable. So we actually run a huge set of trials in industrial areas where we put out 4 different classes of what we call incursions. So we had lots of plastic insects and all sorts of things hidden in trees, and there was a time and motion study, And from this we concluded that there were 4 distinct classes of detectability, ranging from large to cryptic. And so cryptic is describing something that we're not actually expecting to find. And the large samples, we say they're large, but it's better described as something that's visually obvious. So we didn't actually have large infestations or just very, very large objects, which they should be able to find. And so even in best case scenario, if we've got something that's visually obvious out there, we estimate that you've only got a 75% probability on a given zero of actually detecting it. And worst case scenario, you've probably only got 25% per inspection of actually finding it. So it's important to realise that just because a transect intercepts an infestation doesn't guarantee you're actually going to find it. And also with the transects, we ran into some interesting problems in that the model suggests that the longer the transect, the better your detection probability. So we actually had very, very long 500 metre, 1 kilometre long transects because the detection probabilities were fantastic. Operationally, that's just a nightmare. It just doesn't work, not just for the people surveying, but in terms of we're collecting plant species and we want to go to response. Well, we don't know where a particular plant species is in that huge long transect. So operationally, you probably want to use transects that are 50 to 100 metres long. So you're only capturing a smaller amount of plant species. So sometimes models, you shouldn't be led by the models. Sometimes you need to be pragmatic about these things. And again, this is how we deal with variable funding. So quality measurements. Now we're going to use different quality measurements for different programs, but one of them is obviously, well, how many plant species are we capturing and how does that improve over time? If we're only collecting a couple of plant species, well, that's not much use to anyone, but we need to be able to demonstrate that we're capturing a lot more plant species. So this is the database that underpins the spatial data that you saw before. So this is looking at one particular site called Akarana Golf Course. This is one transect, and these are the plant species that are in that transect and the numbers that are there. So you imagine you've got 10,000 of these transects, the amount of, and we replicate surveys of these areas. You imagine the statistical power that we generate in terms of looking at declaring area freedom and things like that, rather than just walking around the site and recording a few plants that we take samples of. And this is crucial. We have to have a system like this if you're going to have a technically robust surveillance program. So one of the measurements we had, and this is only over a 6-month period, is in terms of describing how many plant genera you have and how many plant species you have. So you can see over the 6-month period that we increased both those characteristics. So we can show over time that we're actually improving plant coverage in this particular case. So making informed decisions. So this is that image we saw before, and if I'm a surveillance manager and someone gives me this picture and I go, well, that's pretty cool. Okay, I'm going to deploy some resources there, but I don't actually know if that's 10% of all the risk sites that have been mapped, or is this 100%? And that makes it, I've got a lot of uncertainty about if I'm applying my resources here. Now it turns out that that's actually 70% of all the sites were mapped in this particular area. So the fact that I've actually got a value now helps me realise, well, 70% is not too bad. I can deploy my resources here, and I've got reasonable confidence that I'm doing a good job. But if it was only 10%, I would be really, really uncertain about I'm actually putting my resources in the right place. So again, this is one of those measurements. Each spatial layer, and you saw all those spatial layers that we could use before, each one is a measurement of the information available at that point in time. And it ranges between 0 and 100%, and we can show over time, potentially hundreds of layers of information, how we're improving the quality of our system. This doesn't guarantee that you make the correct decisions, it just shows that you're making informed decisions, or ill-informed decisions, as the case may be. Second example is gypsy moth or GM surveillance, and we run this program in New Zealand because there was a very clear and present danger of gypsy moth turning up in New Zealand. And so this program was actually overhauled in 2003 following a detection, and what was happening at that point in time is we were in what was the phase 2 surveillance, where we're doing something to look for a pest, but we're not doing it in a technically robust way. So what we do is we deploy 1,500 traps nationally. They're baited with a pheromone, a very, very effective pheromone. It's actually more effective than a real gypsy moth female, called the spar lure. So we've actually got a really, really good tool. The program runs for 6 months a year, fortnightly trap clearance, focuses on sea containers and port vehicle pathways, and the important factor here is that we were funded on a levy on sea containers. Every sea container came in, that person was a risk exacerbator and had to pay something like 65 cents per container to fund the program. And the problem with that is it's actually a variable funding regime. And we've seen with global financial crisis and things that the amount of shipping and stuff that moving around the world decreased quite a lot. So we actually got to run in a program that changes in funding levels over time. So we need to be able to respond to that. So this is there's a couple examples of gypsy moth interceptions. First one shows a container, and it's not obvious there, but this had over 60 gypsy moth egg masses on it, and was just about to be passed through the border inspections. All the paperwork was good until someone noticed that there was a discrepancy in the paperwork, and they inspected it. Now, if that had got through, and you've got 60 gypsy moth egg masses there, each with hundreds of eggs, that's pretty much, I could pretty much guarantee that's an established population. The second one shows egg masses that were intercepted on a Japanese car. These were in the grooves in the tyre. Very, very difficult to detect visually, and they were actually hatching at the time of detection. So visual inspections are very notorious for not being able to find things. It's just about impossible. So we know that things are going to get through. For all the things that we find, a lot of things are going to get through, which is why we run the program. Now, again, we're focusing on the pathways, so our sea containers, which are the yellow dots. Transitional facilities handling sea containers are the yellow dots here. Now, what I want you to look at is the black triangles there, and that's the program in 2003 that made the detection. And if you look at that, first thing you'll notice is that it's not associated with our pathways very well. That's because those people didn't have the information at hand describing where these transitional facilities are. So again, they've had to deploy surveillance resources, but not actually have the information there to make informed decisions about it. Now, the other thing is that it seems to be all over the place. There's no rhyme or reason why this trapping system looks like it is. And basically, as I said, it's phase 2 type surveillance. People walking around that find a suitable host and put a trap on it. Now, the detection was actually made at the most southerly trap down there at the bottom. And the implications of that for me were that you've got this trap sitting by itself down there, and it makes a detection. Well, where did that population come from? Or where could the population come from that led to that detection? Because you can see big gaps to the east, big gaps to the west, and you'll see other traps out there on the right-hand side. You'll see 2 traps right next to each other, and yet in other areas there's huge gaps. So this isn't a very, very good program in terms of if we make detections and we make multiple detections, this program actually wouldn't help indicate where a gypsy moth population actually resides. Now the grid cells you see there deployed with the circles in them, that's the program post-2003. So we completely revamped the system and brought in a new way of doing it. And what we tried to do was because we'd mapped all the pathways, we were making informed decisions about where to deploy our grid system. We wanted to deploy a system that is equally spaced, so we're covering areas equally without leaving gaps and without overlapping traps. And even though we end up putting more traps into Hamilton, nationally we end up with about the same number of traps for the same amount of money. So the grid cell coverage is crucial here, and it's similar to what you'd use for fruit fly. But I'd like to see what the fruit fly program looks like in terms of coverage of its risk sites and whether there's gaps and things like that. So we had a lot of problems with the previous type, phase 2 surveillance, and we could demonstrably show that we'd actually improved our coverage and knowledge of what we're actually trying to achieve here. Now those grid cells are actually really, really important, and we made some fundamental changes here. So we use 750 by 750 meter grid cells. That's based on biological knowledge of gypsy moth and how far males will fly to be captured by this pheromone. And critically, grid cells, because they're square, obviously can be scaled up and down depending on our funding levels. So if we needed to go out to 2 kilometer grid cells, we could do that. And in response, they will go down to 50 meters at the highest resolution. So we're using the same method both in surveillance and response. Now, the other critical thing we did is you've got a 750 by 750 meter grid cell. And people putting that trap out there had to survey that whole cell and then make a decision about where they're going to put that trap. That's 56 hectares in an urban environment. You've got to go for residential households, all sorts. You can imagine how long it took to deploy a trap. And then that's not, when they deploy a trap in that grid cell, it's taking no account of where the trap in the adjacent grid cell is. So you can still end up with traps next to each other. You can still end up with gaps. So it was better than just walking around putting some traps out, but we still had some fundamental problems in terms of efficiency. So the simple solution was just to basically put in some targets. And that's what these two circles represent. So the first circle is a 100-meter radius at the center of the grid cell, and the second one is a 250-meter radius. Now, the rules in the gypsy moth standard say when you go to put out a trap, the first thing you do is you go to the 100-meter radius. You survey that, and if you find the optimal host, you put the trap on, you bugger off, and you go to the next trap. So we can end up putting a trap in one of those grid cells, optimally placed, within minutes, as opposed to hours or days. And but that wasn't the only solution, the only advantage we have. So we've divided that grid cell into three distinct areas: within the 100-meter radius, between the 100 and the 250-meter radius, and then outside that area. And obviously, the better, the closer to the center we are, the better. Now, we also have three classes of host plant suitability based on literature. Gypsy moth eats something like 500 plant species in the literature, but we've got a couple of clear winners in terms of its favourite hosts. So, for example, oak and things like that. So we've got three survey areas within each grid cell, and we've got three types of hosts, ranging from optimal, ranging from the second class is okay host. If it was necessary, gypsy moth would live on this, and the third class is completely unsuitable. So we might be talking there's no vegetation there, or we might be talking there's only physical structures in that place. So what we end up with is a 3x3 matrix, which looks like this. So you get the type 1 species, most suitable host, type 2, less suitable, and type 3, which are poor quality hosts. We've got the three survey areas within 100 metre, the 250, and outside that 250 metre radius. Now, as I said, the first instruction for the surveys is survey the 100 metre radius. If you find a type 1 host, put the trap, go to the next site. If you don't find a type 1 host, the instruction is to go to the next survey area. Survey that, and if you can't find a type 1 host, then you look at the type 2 host and so on. So we rank all the combinations of things where they should be applying their traps. And the idea is that if you have to work your way, basically you want to optimize where you put your trap first, and if you haven't got an optimal solution, you work your way down the scale. Now, not only was this obviously an revolution in terms of how we deploy traps, and the trappers loved it, but it also generates a huge amount of information that describes the quality of our gypsy moth program at a point in time. And I'll show you what I mean here. So we've got 1,524 traps deployed nationally, and what we want to do is rank all the traps that are in these different classes, these different combinations. So, for example, if we look within a 100-meter radius, we'll see we've got 42% of all traps were deployed optimally. Really, really efficient trap deployment. But if we go down the bottom, we'll see that actually nearly 92% of all traps could be deployed within that 100-meter radius, which means that in general we've got a trapping system with very, very high spatial integrity. We don't have traps all over the show. They're all pretty much, a large number of them are very much equally spaced. So we're avoiding this gap problem. And if you go across to the other side and look at hosts, you'll see that less than 45% of all traps could actually be deployed on a suitable host. So actually, spatially we've got a really, really good system, but actually the availability of suitable hosts for gypsy moth are the limiting factor to this program. Now this is the national scale, so we can see nationally it's very, very good, but you can obviously look at individual trapping areas, compare each city to each other, see if any particular areas are problematical, and look at revisiting how you site them. And my guess is that this would be a really, really suitable, again, solution for things like fruit fly. And the idea is that this approach is actually a template wherever we're using spatial sampling tools. So, for example, for ants, we might run a 10-meter grid cell, and we're not worried about hosts, we're worried about spatial integrity, so we just have a point at the center of each 10-meter grid cell. And that's what we put the trap. It's very, very simple. And you might only use one target radius, for example. It depends on what sort of host you have. But if we're using a template to design or describe all our spatial trapping programs, then we've got a very, very consistent approach to how we deploy our surveillance programs. And if you're going to be consistent, then you're defensible. You're coming from a robust position. Detection probabilities, fortunately for us, that model has been described a long time ago. And what it says here, with our trapping array, in any given area, we've got a 9% probability of detecting a population of 9 male moths. With 1,000 male moths, we're virtually guaranteed to make a detection. But what realistically we're looking at is around about 60% probability for detecting a population of 100 male moths. And 60% doesn't sound very, very good, but I think it actually is. 100 male moths, that's probably the first generation of males coming out of one gypsy moth egg mass. So if you said I could get a 60%, again, in a response, you're going to run at very, very high densities, and you're going to get these high detection probabilities. We don't know it's there, so to run at 60% of detecting a first gen or second generation, I'd go with that any day. So I'm quite happy with that. And this is the example of scalability. So you saw what happened in Hamilton. We had, I don't know, 100 traps, no, less than 100 traps there. This is what it looked like in the eradication program, where you had 1,200 traps deployed in the region. And the Précis map on the right-hand side shows that the 50-metre spacing. So they've got more traps running around this one detection, and it was only one moth that was detected. It's actually run more traps in a surveillance program than you run nationally. So you see this issue in terms of scalability. And they were also using a grid system, not the same as us. They were, but I think they probably would in the future. So this is scalability in reality. This is what it looks like. And you just, this costs a lot more money than we run the program for. I think under $20 million, but you're talking a lot of money. Whereas we can run our program for a small fraction of that. So let's summarize. It seems that some robust principles of biosecurity surveillance can be identified, and as I've hopefully shown, can be applied in real-world situations. And these can be used for very different surveillance approaches. We talked about broad spectrum, and we talked about pest-specific programs. So hopefully these will serve as a template or a guide to helping people who need to design surveillance programs. And we'll briefly talk about NT surveillance strategy. Well, I think let's be fair, we are in the phase 2 situation because we have variable funding, we have stop-start funding, and we haven't had the time or capability to develop a robust surveillance system for plant pests. I think we can, and obviously we're going to need more money, but that's a discussion for another time. But the first requirement, the first thing you do is you map out the spatial risk. We need to understand what we're actually dealing with and the scale of it. So where are all the caravan and camping grounds in the state? We don't have that information in hand. So at the moment, we're surveying a subset of all these risk areas, but we don't know what we're actually missing. So we're running under that, I'm deploying limited resources under high uncertainty, which is, you want to be deploying limited resources under high certainty. You actually know what you're dealing with. In the future, we also need to get a handheld data capture to improve the quality of systems. And what I've been doing lately is basically collecting data to map out these spatial layers. So we can sit down, people who need to be involved can sit down and look at these maps and basically decide what we're going to do. And it's important to realise that we don't need all these spatial layers for every surveillance program. You turn on and off the layers that you need for a specific purpose. But this is the sort of data we can collect, and I am collecting at the moment. And some of these look like strange ones like supermarkets, but supermarkets are high-risk sites. They carry a lot of fruit and have a lot of wooden pallets and stuff like that. So this is the first, and this is the easy, and this is the cheapest stage in developing phase 3 technically robust surveillance programs. Again, lots of accommodation layers, and probably NT is probably unique compared to other countries and states in that trade is probably a lesser risk than tourism, in my opinion. We just don't deal with the volumes of sea containers that other places have. So I think accommodation is going to be one of the big ones that we deal with. Well, thank you very much for your time, and just some acknowledgement there of key people who contributed to this program, particularly Quentin Hagan, who I developed the high-risk site surveillance program with as a GIS mapper, and it was a two-man effort, but hopefully that was useful for you, and that's the end of my talk. Thank you for coming.